Hello, welcome back. Today I'm going to show you how to take a regular egg straight out of the refrigerator and turn it into a bouncy ball that does not break when you drop it, but rather bounces around. And along the way, we'll talk about the chemistry of acids and bases. We'll also talk about elastic and inelastic collisions and do all sorts of really cool things after we turn this egg into basically a bouncy ball. All right, well first, let me remind you what happens. If you take a regular egg and just sort of drop it, what happens? Well, you see the egg cracks, right? The shell itself is very, very hard, but with rapid impact there, it can crack. Now, the shell itself is made of something called calcium carbonate, but that calcium carbonate can be dissolved away. And if you think about peeling an egg, underneath the eggshell actually is sort of a membrane that actually is the inner membrane surrounding everything inside. So that inner membrane is underneath the hard outer shell, which again is calcium carbonate. And so by dissolving that away, what we're left with is the inner membrane. So let me show you what that looks like. These have been soaking for a while. I'm going to actually show you exactly how to do this. Basically what you do is you soak them in vinegar. So vinegar is an acid, and that acid reacts with what's in the eggshell there. So let me show you what happens here. Notice I have a couple here that have already kind of broken here, but if I take this one, and these have been soaking for a few days, usually it takes 2 or 3 days, and put that aside there, and just kind of put it on there so you can sort of see what it actually looks like. Right? Let me try to clean it off a little bit here. You can actually run it under water, you know, and so on and so forth. Let me show you what the two eggs look like there when you compare them to one another. So basically, this is a little bit of a larger egg. This is from a different batch there, and this is sort of a regular large egg, and this is sort of like an extra large egg. The small egg, of course, is unchanged, and so it's very hard. But the large egg, if I put this here and show you, you can sort of bounce it up and down like a bouncy ball. Notice it's starting to crack here because this has been in here quite a long time, but you can still see the bouncy nature of the egg there. It's really cool. Of course, if you drop it high enough, it will break, it will snap, and I'm going to do that for you. But before we do it, let's play around with it.
Now, the first thing I did is tried to drop it on its side, which definitely looks cool, but gave me the least impressive bounce. But you can still see the energy being absorbed by the internal structure and the membrane before it bounces. Next, I dropped it on the fat end, and you can really see the waves in the membrane and the compression and the ripples at the opposite end whenever the egg gets to its maximum compression. Finally, I turned it over and dropped it on the small end and raised it as high as I could before breaking. Take a look at the ripples. You see the deformation is absolutely incredible. It seems to be maximum at the opposite side of the egg. Here's a close-up shot. Look at the ripples that are happening there. It almost looks like plastic or rubber. Definitely not a hard shell.
So since we've actually already got this one sort of halfway broken, let's drop it from a little bit of a higher height. 1, 2, 3. And you can see that everything's intact on the inside.
Now I just had to catch one of these breaking in slow motion. It splits. Everything on the inside comes spilling out. And of course in slow motion it looks absolutely incredible. Here's a close-up of the actual split itself. You can see it rip from bottom to top and just spill out and explode. Look at the membrane after the fact. It looks soft and stretchy instead of hard.
Now let's take a look at what we have left over here. This is the membrane I was talking about. This white stuff here, there's nothing hard left behind. Once you have dissolved the eggshell away, what the inner membrane here is sort of like unaffected by the acid, and it's protecting the delicate yolk in the center. In fact, this yolk feels a little bit weird too. If you pull that up, wow, that feels a little bit weird. I mean, the white here looks similar to what you might expect, but the yolk has it's almost like a gummy texture to it. I'm squeezing it. Look at the way that looks. It's just so weird. It's very, so I guess the reaction does penetrate the shell a little bit into the inside here. And just for comparison, we have a fresh yolk here, which you can see behaves nothing like this. It's very gooey and so on and so forth, whereas this one It's sort of like congealed into a mess here, almost like like I say, a gummy bear sort of texture to it.
Now I picked up the super small metal, high quality actually, bow and arrow with these tiny little 6-inch little arrows that I can use to shoot at high speed at these eggs. I originally got it for shooting water balloons, but I really want to see what happens when you shoot a hard egg and one of these soft eggs. So here's an old shot of me shooting these water balloons, and it took a while for me to get the hang of exactly how to fire it. You have to hit it at the right spot and the right speed or it just bounces off. After gluing a needle at the end of the arrowhead, it made a clean insertion point and exit point with an incredible shot of this balloon disintegrating in slow motion. Unfortunately, I couldn't get it to go through the balloon without rupturing. I think the impact is just too violent and always rips the rubber. Here's an incredible shot showing the impact point, and we can see the rubber fracture all the way around, rip apart, and then the entire process happens in a fraction of a second. Here I shot it again in a little slower motion of 3,500 frames per second. You can really see the rubber snap at the impact point, dragging the water droplets around with it, flinging them around essentially, and then the bulk of the water in the inside is mostly unchanged and then falls down under gravity. Okay, here's shooting egg number 1 here. Notice how strong this eggshell is. Even with this force of impact, it chips part of the eggshell out, and then you can see the fragments fly away, and the egg just kind of gets knocked off of the pedestal, but more or less it stays intact. It was actually a little frustrating here. I was trying to hit the egg dead on, but I kept hitting these glancing blows in the beginning. But it actually looks pretty cool because it tears part of the eggshell off, which is quite strong, and in this case spins the egg around, flinging part of the insides out. Here I finally got a dead-on shot straight to the side of the shell, and it goes in a clean insertion, cracking the shell, and a clean exit. Notice the propagation of this crack from the point of impact all the way down to the bottom. Notice here that the point of impact has a lot of material ejected, and when the arrow flies out the back end, it drags out the yolk with it. Clean insertion, clean exit. Here's my first attempt at shooting one of these soft eggs with the shell dissolved. Notice how there's a clean insertion and a clean exit, but there really aren't any cracks forming because there's no shell. This is just the inner membrane here. And I think it really shows how much that outer eggshell really protects the inside of the egg, because without it, it's totally vulnerable. Also notice the ripples and waves set up in the membrane directly when the arrow goes in and out. You only see that when there's no shell present and we're hitting the membrane. Here's my second attempt shooting one of these bouncy eggs. Clean insertion and clean exit. Again, no cracks forming, and notice the waves and ripples in the egg membrane as it passes through. In fact, it was such a clean entry and exit point that the egg really didn't drain out. It kind of stayed intact. So I went ahead and set up and shot it again, trying to get a glancing blow to try to rip it open on the side. And this is where I got what I was really shooting for. I wanted to see the flexible membrane punctured from the side and sort of ripped open from the side so that you could really see the difference between this flexible membrane and the hard outer shell, with the inside then flowing and kind of like dripping out through the exit hole. Pay close attention to the ripples in the membrane as we go on this glancing blow. It almost looks like ripples on the surface of a pond. And this is the best shot of the series. You can see that as we slice through the membrane, we literally rip it completely open, which is what I was really going for. The yolk spills out, and you can just see how thin this membrane is. I believe I left this one in the vinegar the longest, so it had the least amount of eggshell and almost pure membrane, which is why it splits so nicely.
I noticed something really interesting. So here is a laser. This is a green laser right here. And when you shine into these eggs, they kind of scatter the light on the inside and kind of light up, which is kind of interesting. Maybe able to see a little bit better with the red laser I have. Yeah, you can see that a lot better. Check that out. So it kind of glows like this. Now this led me to wonder what would happen if I used my really powerful laser here. So these lasers here that I have are just, a handful of milliwatts here. This laser that I have right here is, to my knowledge, the most powerful consumer laser you can get, it's a 5-watt laser, so 5,000 milliwatts. So this thing has actually got enough energy density to burn paper and such. So I want to do that for you real quick, and I want to see if I can slice this egg with it. I don't know if it'll work because there's so much water inside the egg, but we'll try it. So let me just put that off to the side here and show you what happens. First, you have to have safety glasses for a laser of that power. So there we go there. It's got a safety interlock here. And let me just show you what happens when you use this laser on a piece of paper. So just hold it in one spot and you can see you're burning that paper just with the power of light. Here's a different color piece of paper. I don't really want to catch it on fire. I just want to kind of scorch it. Okay, very cool, right? Now, just to show you the kind of power you're dealing with here, here's a regular match head. Nothing special about it. And I will use this laser to light the match head. And that is cool enough. That is cool enough where I actually want to do it one more time. 1, 2, 3, here we go. Let's, just for giggles, let's just try it in this region where I kind of wiped away some of the outer coating there. And the laser light is absorbed mostly where there's black. So I can't really make it super black, but I can add a little something here.
Now this is about 20x speed. I actually held it on here for a minute or so. It smelled nasty, but it didn't burn.
Now they say there are no failures in science. I mean, this is something we have to talk about, right? Obviously it scorched it. It absolutely looked like it was gonna burn all the way through. Why didn't it just like explode this egg or slice it open like you might see in Star Wars with a lightsaber or whatever? Well, it's because there's a lot of water in the egg. I mean, it's thick, gooey water we call yolk and white, egg white, but it's a lot of water. So as soon as the outside surface of the egg heats up a little bit, then the water on the inside takes the heat away. And so because of that, the surface can never really get hot enough to truly get sliced open. Basically, water is a really, really, really good absorber of heat. Same thing will happen if you take a water balloon and hold a candle under a water balloon. The water inside will absorb so much heat that the water balloon, it will take either a very long time to pop or it won't pop at all. Now I want to show you how to actually make this. The first thing you need to do is just grab an egg, doesn't matter what kind of egg, this is a regular large egg, put it in a container, and then grab some household vinegar. I'm going to show you the chemical reaction in just a minute for that, but watch what happens when I pour the vinegar in. So here we go. I'm going to try to cover up the egg like this. Now let's just wait just a minute. Obviously it takes a few days for this to actually happen, but you can start to see some interesting things within a few minutes.
So I set up a time lapse to capture this process. Even though the reaction seems pretty slow in real time, when you look at it in time lapse, you can really see that it's kind of violent with a lot of carbon dioxide gas produced. The egg begins to float because of all the gas bubbles attached to it on the left. And notice I have an egg on the right that's only halfway submerged in the vinegar. And you can see the discoloration start to happen as well. About a couple of days into it, it turns from this bright white to more of a dull brown color. And then on the right-hand side, when you see the egg half submerged, you'll see that the vinegar begins to really evaporate after a while and really starts to leave behind this dull, brownish looking membrane that's very, very soft to the touch. And then notice that suddenly after a few days, the vigorous agitation and the moving around of the egg just stops because the carbon dioxide stops getting produced and it stops pushing around the egg. And then you really see the evaporation take place and then the process concludes. Now I want you to keep your mind on the pink logo printed on the egg here and watch it fade over time as the eggshell literally reacts with the vinegar. I really wanted to get a super close-up shot, so I put my macro lens on the time-lapse camera, and I think this really brings it home that a process that seems very gentle with little bubbles that don't seem to be doing too much in real time, when you speed it up and really look at it over a period of 3 or 4 days, you could see that all of this activity is going on here. And in fact, in this case, in order to do this, I had to weigh the egg down on the bottom there and keep it at the bottom. So what I did is I super glued some coins to the bottom here just to keep it down in the bottom of the vinegar so we could watch this process unfold. Just to recalibrate you, here is a handheld shot that I took with my phone while the time-lapse was actually going on. So even though in the time-lapse it looks so violent, like some sort of volcanic eruption or something, in real time it looks like nothing is happening at all, but the process is going on slowly all the time.
Now, before we go any farther here, these are some that I have already sort of dissolved and already broken for some of the slow motion footage, and they kind of sat out on the counter. This is not the eggshell. This is the membrane left over when you let it sort of dry out. You can see how crumbly it is. It just sort of breaks. Very different than an eggshell. If you peel an egg, you know it doesn't quite break like this. This just totally turns to dust. Now, if you actually take this and put it back in either into water or into the vinegar bath, then what you're going to see is one that I've done right here, where that's exactly what happened. I took it off the counter, which is very dry, and then I put it right back into the liquid, and you can see that it turns into the stretchy membrane again. So it's sort of dehydrated here, and you can rehydrate it, and it turns into this nice stretchy protective membrane. So what's going on here is vinegar is an acid, a very common acid that we used to cook and we used to clean and so on. Now, the thing you need to realize about acids are defined to be chemicals so that when you put them in water, they donate a proton donor. There. Another way of saying is a proton is it's a hydrogen ion. Remember, hydrogen is the very first element on the periodic table. It has one proton and a single electron going around the outside of that hydrogen. So if you say that an acid donates a hydrogen ion, what is a hydrogen ion? Well, it's just a hydrogen atom minus an electron, which is just a proton. So there's two ways to call an acid. You can call it a hydrogen ion donor. That's what that means. Power of hydrogen is the pH scale, pH power of hydrogen. Or you can call it a hydrogen ion donor or just a proton donor. The more protons it gives in solution, then the stronger the acid, right? So there's hydrochloric acid, there's sulfuric acid, there's nitric acid. They all donate protons or hydrogen ions in a water solution, right? Now, those acids react with various things. They can react with metals, they can react with bases. Base is sort of the opposite of an acid, whereas an acid donates protons or hydrogen ions. A base is something that reacts with hydrogen ions or protons. So whatever reacts with an acid is what we call a base. Now this eggshell here, if you look carefully, even after just a few minutes, you can see that bubbles are starting to form right there on the surface. In fact, you can kind of see some of the bubbles kind of bubbling up here on the surface there. So what's happening is the calcium carbonate, which is what that eggshell is made of. By the way, that's the same material in seashells, you know, like big shells you hold up to your ear. That's all made of the same stuff, calcium carbonate. It has calcium in it, it has carbon in it, and it has oxygen in it. That's the carbonate ion. Right? So calcium carbonate. So calcium carbonate is acting kind of like a base, and it's reacting with the acid, with the proton specifically, and it's forming carbon dioxide. That's the bubbles that you see. Also, it's forming water, and since everything's in a water solution, you don't really notice the water that's forming as well, but water is coming out of it as well.
I want to talk a little bit about what the eggshell is for, and let's put some eggs in a vacuum chamber to see what happens.
It obviously needs to be strong because birds, will sit on their eggs, and so it has to be strong enough to withstand that. But also, it acts as a semi-permeable membrane that allows gas to go in and out, like oxygen to go in, and carbon dioxide to come out, while keeping the liquid held on the inside, the yolk and the white that's on the inside. So it allows gases to transfer back and forth, a basic form of respiration before the chicken is fully developed or before the bird is fully developed. It's allowing CO2 and oxygen to pass back and forth through microscopic holes in the egg there. And the egg is obviously very strong. It's made mostly of something called calcium carbonate. So some calcium atoms, you think about calcium making your bones strong, right? Carbon, oxygen, so calcium carbonate, right? Now it's very, very strong. If you have your hand here, now if you're a really strong person or really practice, or if you cheat a little bit, you can get this to happen. But if you take an egg in your hand like this, and don't put a pressure point with your finger, but just wrap around it and squeeze. Most people cannot break an egg. If you do it, be careful, do it outside, do it over a trash can so it can make a mess. If you put a pressure point, if you put your thumb here and push with your thumb, you can overcome the strength and break it. But I'm squeezing pretty strong, maybe not all of my strength, but a good chunk of it, and I can't break it. And the reason is because the shape of the egg is this weird ellipsoid, not symmetrical, but it's an ellipsoid. And so as I squeeze, then every part of the shell, or most of it, is under compression. And this eggshell, when it's being compressed along the direction of the shell, is very, very strong. But if you put if you bang it against something hard like this, then or if you push with your thumb with a very high pressure here, then you're pushing in and you're deforming it inward, and you're almost, instead of compression, you're putting it in tension. You're pulling it apart. That's what tension is. And these things are not very strong in tension. They're very strong in compression though. So if you put your hand around evenly and squeeze, then you usually can't get it to break. But if you put your thumb and squeeze really hard, you can. The other thing you can do, here I have a dime here. And so if I just put this in my hand, see, I can't really break it too easily here, but if I put this here and then do it like this, and I'm putting a pressure point, I'm essentially concentrating a lot of the force on the edges of this dime here, and then when I do that, very, very easily, I broke this egg here. Give it a try, but be careful, it's really messy.
I started shooting these high-speed shots of eggs cracking and dropping into the bowl, and when I started looking at the footage, it just absolutely mesmerized me. So I'm going to go ahead and leave them in here. Basically, these shots range from about 1,400 frames per second all the way up to maybe 4,000 frames a second, depending on the shot. And it's almost like these eggs, when they're falling, it's like they're in a different universe of their own. We see this stuff with our eyes, but when you slow it down, you can just see every little drop, the surface tension, the viscosity. You see details that we just can't see with our senses. And so it's fascinating to me. So I hope you enjoy these. Now, for the photography nerds out there, when you shoot really high-speed footage like this, it's a specialized camera, and the frame rates are so high that you need a ton of light. My normal studio lights is not even close to what you need for this. To get these shots, I have to have three 300-watt LED spotlights, essentially. So about 900 watts just in lights, and these lights are not omnidirectional. They're spotlights that go directly on. So it literally would blind you if you looked at these lights with your naked eye. But the shots I think that we get as a final result are amazing.
All right, this is going to either make a huge mess or do absolutely nothing at all. Let's take a look. Eggs, trying to scramble them in a vacuum chamber. Will they boil or not? 3, 2, 1, here's the vacuum. All right. We're at 3/4 of an atmosphere. And now we are at 1/2 of an atmosphere. Okay. Passing half an atmosphere. I see some movement in there. Maybe that was just my imagination. I thought I saw some movement at the bottom there. Okay, now we're approaching 1/4 of an atmosphere. I see some bubbles coming up. I do, absolutely. It's not my imagination. So we see some bubbles forming. Let's see, by removing the outside air pressure, how messy this gets. I have no idea. Okay, we're past 1/4 of an atmosphere. Got some big bubbles in the center. Ooh, looks like a lot of bubbles are forming. Okay, we're almost to the limit of what this vacuum pump can actually do. Let's just keep pumping. Oh, it looks like the eggs are swelling up. Oh my goodness. I think this might make a big mess. Oh, it's definitely swelling. So whatever dissolved gases were in there are coming out and making bubbles. And this is going to make a mess. Ooh. Okay. And right over the top. Yep. we're in a mess territory here. Wow, it looks very foamy. Almost like a curtain. Wow, check that out. That is really neat looking. Oh my goodness. So why is it boiling? I mean, basically that's what's happening. Is it's kind of boiling and also dissolved gases are coming out. Why is that happening? Well, because liquids are easier to boil at a lower outside pressure because it's easier for the molecules to escape and to go off into the outside environment because there's less pressure from the outside. Wow, this thing is like baking a cake. Oh my goodness. You can see the structure of all the bubbles there. So we have some dissolved gases coming out. We have some water that's kind of boiling and making a bubbling kind of sensation here. We have like a caldera or some sort of valley in the center of this thing. I'm going to be scrubbing this thing for days. Okay. All right. And we're going to let the air back in. 3, 2, 1. What happens there? And it just collapses.
And here is that footage sped up so you can see the whole process a little faster.
Consistency is the same, more or less. Let's touch it. It's nice and cool. From another video I've done, I've already talked about that things get colder when they actually boil. We don't notice it on the stove because we're adding heat from the bottom to get it to boil. And so we kind of think of boiling as something we add heat to and it gets hotter. But the act of boiling itself, the hottest molecules, which are the most agitated, actually escape and they leave the surface. Like boiling water, the steam comes off, leaving behind the cooler bulk liquid behind. So a thermometer in boiling water in a vacuum actually goes down because everything left behind is cooler than the hot particles which have escaped. So the reason this thing boils and we've scrambled eggs, so to speak, in a vacuum is because the outside air pressure is lower. So it's easier for whatever water molecules are in here to escape because the outside air pressure is lower. And because of that, we get the boiling process. Of course, it makes all the foam because we have a lot of elasticity in the egg yolk. And so it kind of makes that foamy situation that we saw. Now, before I get into the chemical reaction, because it's pretty easy to understand and I think pretty cool to understand where it comes from, before we get into that, let's talk a little bit more about dropping the egg on the surface there. And you can see how in the slow motion it deforms and then bounces back up and kind of just bounces all over the place there. Whereas when the hard eggshell hits, it just cracks and goes everywhere there. So in physics, we study collisions a lot. And, you know, we learn what happens if you have some ball with some mass and some initial velocity. It's going this way. And then you have, call this mass number 1. And then you have another ball, mass number 2. Maybe it's stationary to begin with, or it might be racing towards the first one with a totally different velocity. We call it V2. Now, what we want to know in physics is we want to know what happens after the collision, right? And we have so many different avenues for wanting to know this. In a car accident, what's going to happen to the two cars? That's obviously pretty important to design safe vehicles. Particle accelerators. You might be accelerating a proton and some heavy ion. What's going to happen? Which way is everything going to go and at what velocities are they going to go? So you talk about conservation of momentum in collisions. You also talk about conservation of energy, specifically kinetic energy, right? So remember back from physics, we say that the kinetic energy of any body is 1/2 mv squared. Now, this is classical physics. We're not talking about quantum mechanics. In real life, every quantum object, anything made of atoms, ultimately is quantum object at the fundamental level. And so the energy relations are a little bit different. This is called classical physics. For things like eggs and rocks, it's a pretty good approximation. So 1/2 times the mass of the body times the velocity squared. That's how many joules of kinetic energy. And we always talk about the law of conservation of energy. Now, in collisions, when two bodies are colliding with one another, there's really two cases to think about. The first case is if you have like a billiards or pool table with very hard, rigid balls. Those balls, whenever they smack into each other, the kinetic energy before the collision, we say, is conserved. In other words, before the collision and after collision, the total kinetic energy of everything happening remains unchanged. So that means if I know the velocity of the incoming ball 1 and its energy, 1/2 mv squared, and I know the kinetic energy of this one, 1/2 mv squared, after they collide, if it's what we call an elastic collision, then the kinetic energy total before the collision and the kinetic energy total after the collision has to be unchanged. And all that means is that during the interaction, when they touch here, that all of the kinetic energy of the motion of each of the individual balls, it basically goes into the motion of the final velocity of the balls, whichever way they go. Also, don't forget that I've got them coming straight at each other, but they can be going off at different angles as well, depending on if it's a glancing blow or not. So basically, elastic collision is what you mostly study in physics. Whenever the two bodies, we say the energy is conserved, right? But there's one big exception to this. It's something called an inelastic collision. And that would be if one or both of the two bodies basically either get stuck together so that maybe instead of ricocheting off, so that we could say the energy before and after is unchanged, maybe they get stuck together, like two balls of clay. You smack them into each other and then they kind of get stuck together, right? Or in the case of this bouncy ball egg, that's why I'm bringing it up, when you drop it, you see how it deforms and then it springs back. You see, in that case, the energy of the motion that the egg had when it hits the surface of the table, some of the energy doesn't just go into the final velocity of the thing bouncing off. Whenever it deforms like that, some of the incoming energy of when you dropped it to begin with, some of it goes into the deformation of the solid. So I talk about things like clay or Play-Doh hitting each other. Talk about this bouncy egg. Talk about a bouncy ball. When you throw a bouncy ball, it gets deformed as well. And so we say that the kinetic energy before and after the collision is not conserved. But that's a little bit of a lie. It really is always conserved. It's just that some of the energy goes into basically heating up the material because it gets smushed. So if you could take the bouncy egg there and measure its internal temperature before and after you drop it, the internal temperature would be slightly higher because some of the energy went into physically squishing the thing, and then that agitates everything inside and it goes into the thermal motion of the gooey liquid on the inside, right? So if you have hard, rigid bodies that don't deform, we say it's elastic. 1/2 mv squared before and after, everything has to add up because we say in that case that the internal structure doesn't gain any energy from the collision. It just goes into the exit velocities of everything. But if you have Play-Doh, a gooey ball like this, a bouncy ball egg, or another example would be two cars that collide. You see, cars are designed with crumple zones. So they don't just bounce off and ricochet, they're designed to crumple, and some of the energy goes into the crumpling of the structure of both cars. So we say it's an inelastic collision. That just means the velocity of the two bodies after, when you add up the energies, they don't seem to quite add up. Where did the energy go? Energy is always conserved. It just means that in an inelastic collision, some of that input energy goes into either crumpling the hoods of the cars, or in the case of the egg, it goes into deforming the egg, slightly raising its internal temperature, or some other mechanism like sticking together, basically that causes the thermal agitation of the atoms, like if you have two balls of clay and so on. So I just wanted to go over inelastic and elastic collisions because this is a perfect example. And if you think about the inside of that egg being like a gooey, viscous liquid, we say it's mostly water, but clearly it's thicker than water. It's more like syrup, right? There's a very high viscosity, which means internal friction. When that internal liquid begins to swirl, there's a lot of internal rubbing because it's not water. It is water, but it's thicker than water. And so there's a lot of internal vortices and all kinds of things going on if you had X-ray vision and could look on the inside. That's dissipating some of the input energy from dropping it. All right, so now real quick, I want to write down the chemical reaction to what's going on to dissolve that eggshell because I think it's interesting and it's a good practical example of acid-base reactions. So what vinegar is called acetic acid. So it's CH3COOH, and we say that that's an aqueous solution. That just means it's dissolved in water. Now acids, when they dissolve in water, they donate protons or hydrogen ions. Now there's some hydrogens right here, there's 3 of them, and there's another hydrogen here. Now these 3 hydrogens are pretty tightly bound to the carbon, so water does not cause these guys to dissociate and to go into solution. It's this hydrogen on the end is actually the one that detaches and begins to go and react with everything. So keep that in mind. I'm going to talk about that in just a second. And we're going to add to that the calcium carbonate. So that's CaCO3, and that's a solid because that's the white eggshell. So this is all that we're doing. We put these guys together. Aqueous means it's in a solution of water, but in reality, keep in mind that this hydrogen ion pops off. This is an ion, and then the hydrogen ion's floating around in solution, and then it begins to react with whatever is there. And what we get on the other side of that as a final product is this, this hydrogen pops off. Keep that in the back of your mind. The calcium goes, and we write it like this, CaCH3COO, like this, and this is an aqueous solution. And then what we also get is CO2, that's the bubbles that we see, which is a gas. And then we also get H2O, which is a liquid. I should have probably written it all out off to the right there. The first thing we have to do is balance this chemical reaction. This is what's really going on here. And the way you balance it, I'll just give you the answer. There's a 2 right there. All right, let's check and see if this is balanced. Here we have 2 carbons, 2 more carbons, and there's another one. That's 5 carbons on the left. On the right, we have 2 carbons, that's 4, 5 carbons on the right. That's correct. For hydrogen, 6 hydrogens, plus 2 more here is 8 hydrogens on the left. Here we have 6, 2 times 3 is 6, and then 7, 8, so 8 hydrogens, that's correct. We've already taken care of the carbon. Then we have 2 oxygens here, and then 2 more is 4 oxygens, so that's 4, and then there's 7 oxygens altogether. So 7 on the left. On the right, we have the 2 and the 2, that's 4, 5, 6, and then 7 oxygens on the right. So we went element by element, and we know that everything's balanced because we have the same number of atoms on the left and on the right. But this chemical formula is a little bit misleading because even though it shows what's really going on, we make the CO2 and the H2O, it makes it sound like this compound here is like formed like some solid or something, but really it's an aqueous solution, and it's basically dissolved and dissociated here. So they're floating around as ions here. So what you can actually do is you can simplify this and make kind of like what we call a net ionic equation, what's a little bit easier to understand, and throw away the things that aren't really participating. So what you can really say is you can start with the calcium carbonate, CaCO3. And really, what's really going on here is, even though this is all in there mixed in, notice that this ion's floating on the left and it's also floating on the right. So it doesn't, this ion here that's left over from the acid is really, since it's on the left and on the right, it's not really doing anything. So we can remove it from the equation. And we can say that these 2 hydrogen ions is really what's doing anything in the solution. Okay. And then what we can say, I can say this is aqueous. We have this calcium ion that's floating around, and then we have H2O, and then we have CO2, something like this. Now we have to double check it's balanced again. We have 1 calcium, Yes, it's an ion, and it's not an ion here, but you get the idea. Calcium, the atom is balanced. Then we have a carbon here, a single one, a carbon here, that's balanced. We have 3 oxygens, and there's 1, 2, 3 oxygens right there, and then we have 2 hydrogens and 2 hydrogens. So some are ions and some are not, but the atoms are balanced. Now the difference between this giant equation and this one is that we just basically throw away some of the stuff that's not really participating. When this goes into solution, the hydrogen ions is really what's doing the reacting. This ion is just sitting here, and it's not really doing anything because it's still dissolved in solution, so we remove it. What's left over is the hydrogen ion here. This is here, and on the right-hand side, the calcium is floating around in solution. That's something new and different than what we had to begin with here because it split that apart, and it makes the water and the carbon dioxide. This is easier to read what's really going on because the calcium carbonate is basically reacting with the hydrogen ion, and you can see more clearly what's going on. The calcium just stays in solution as an ion. It's just dissolved. Right? And then what's happening is one of these oxygens is popping off, leaving CO2. That's the gas that comes out. The one oxygen that pops off bonds with this, H2O, and that makes the H2O. So what's really happening is this pops off and stays as an ion. One of the oxygen leaves, leaving CO2, that's the gas. The oxygen that popped off, so to speak, bonds with this to make the water. So ultimately what's happening is when you take the eggshell and you put it in this acid, the proton from the acid is reacting with it. That's why this is considered a base, and then this is considered, of course, the acid. And what you get is water and carbon dioxide, and that's what we see is the bubbles in the solution. Now, I can't say it's a super vigorous reaction. If I had a stronger acid with more protons, it would react more vigorously. But what you see here is what I did today is just with supermarket vinegar there, which is acetic acid. And if you've ever made a baking soda and vinegar volcano, it's a very similar reaction because vinegar, of course, is the same acetic acid that we have. You aren't going to be putting it with calcium carbonate. You'll be putting it with sodium bicarbonate, which is the baking soda. But similar reaction is what's happening. When you look at the chemistry there, it's making CO2 gas there, which is very vigorous and kind of goes up and makes your nice volcano. So I thought this is pretty cool. Grab an egg, put it on the counter, pour some vinegar, wait a few days, dissolve the eggshell away. It's not really dissolving, it's reacting, and it's basically going into CO2 gas there. And I guess I'll leave you with one question or one observation, is that I mentioned in passing that seashells from marine life is made from calcium carbonate as well. So if you have a lot of acid rain or acidic oceans, you upset the balance there and you have too acidic of an environment, then what happens is those marine animals lose their shells. They literally reacts away. So that's kind of like you hear in the news, like acid rain or whatever. Part of that is dissolving rocks and also dissolving, marine shells and such. So it can affect the environment, this kind of reaction, this kind of chemistry. Well, I hope you've enjoyed it. I hope you liked looking at dissolving the eggshell, seeing what was left behind, and doing all the things we did, really looking in slow motion and seeing the deformation there, talking about elastic and inelastic collisions, shooting it with a bow and arrow, just playing around with it, trying to slice it open with a laser, and then realizing that you can't really do that because there's too much water in there, and so on and so forth. So drop me a line, please, and let me know what you think. I'd like to know, did you find it interesting? Did you find it boring? I'd really like to know what you think. So please, I read every comment, and always remember to stay curious.
Learn anything at mathandscience.com.